Okay, this video we're going to still talk about refraction, but we're going to get into specific kinds of refraction. And by that I mean we're going to start talking about lenses. So, we're still bending light. We're still refracting. And I want to go over a simple example really quickly. Simple refraction that we were talking about, and I want to emphasize the very important things that I need you to know. If you are struggling with the math on Snell's law, that's fine. That's not near as important as the big ideas here. So, here's our surface. It's our interface between air and plastic. Air has an index of refraction of 1, plastic index of refraction 2. And what we see as we go from air into plastic, that the light is slowing down, and so it turns more into the medium. It's going to bend towards the normal line because it's going from fast to slow. So when the light slows down, it bends towards the normal line. And just to remember, our normal line is drawn perpendicular to the surface. The normal is always perpendicular to the surface. Normal and perpendicular are the same word. So, you find the interface between your two mediums, where they meet, that's our surface, and the normal line is going to be at a right angle to that, at 90 degrees to that. That's what it means to be normal. So, that's what happens when we go from fast to slow. Oh, real quick. Always draw your normal line. When you're doing refraction, always draw the normal line. And the normal line is important because when we talk about angles, when we talk about bending towards the normal or bending away from the normal, angles and that bending all have to do with the normal line. It has to be there. Okay. So, here let's say we go from plastic, where n equals 2, into air, where n equals 1. When that happens, we bend away from the medium. With respect to the normal, light bends away from the normal this time. So when we go from slow to fast, light bends away from our normal. The exception to that is that light will reflect once we hit our limit, once we hit that critical angle. Critical angle is the last possible refraction where that we have, where the light is refracted perpendicular to the normal line, parallel to the surface. Once we get past that, we're just going to totally reflect on the inside. That is simple refraction. We're going to move on and talk about lenses. So here's a very simple drawing of a lens. We're going to have air there. We're going to have glass right there where n equals 2. It's I guess, just like our plastic. And we're going to look at how light coming into that piece of glass bends because of the glass. Now, the first thing that we're going to run into is that surface. Now, at that surface, we don't have any bending. We don't have any bending because the incoming ray hits the surface at a 90-degree angle. When that happens, there's no bending. Okay? That means my angle with respect to the normal is 0, and it means we're not going to have any bending. And we saw this in class when we played with those big lenses. Now, what's interesting is what happens because the surface of the glass is bent. We have to redraw our normal lines. Okay? Now we want to redraw it so that it intersects the surface at 90 degrees. So it's going to change. Because the surface bent, our normal line is not where it was before. Now, that's our normal line. Because we're going from glass into air this time, we're speeding up, which means we're going to turn away from the normal. So let's see what that looks like. Now, that is without it bending at all. If we're going to bend away from the normal, it's going to go lower than that line. That's how it's going to bend. That is bending away from the normal line. It speeds up, so it bends away. We're using that same idea that we've done in refraction. We're just looking at how it bends away. The same thing is going to happen for the bottom line. It's going to bend away from the normal. And then that middle line doesn't do anything because, again, it hits the surface at 90 degrees. There's no bending going on. So, for this particular lens, this shape, causes light rays that are parallel to converge at a point. We call this point the focal point. Now, before we get away with ourselves, that's our focal point. This shape causes parallel light rays to converge at the focal point. So we call it a converging lens. It causes light rays to come together. The shape is convex. It's bending out. That's a convex lens. We'll call it a converging lens. And a converging lens has a positive focal point. We will do a little bit of the lens equation, and so it's important there. But for us, the focal point is in a normal spot. That's why it's going to be positive. Let's look at a different shape. We have air and glass, same indexes of refraction, and then we have some parallel light rays coming into it. And we'll notice this kind of caves in a little bit. We're going to call it concave. Now, just like before, because those light rays hit the glass at that angle, there's not going to be any bending for the beginning part. Now the second part, we have to redraw our normal line. Now the first one goes through because it's hitting at 90 degrees, but for the other two, you can see how the normal lines point in a little bit. Now, for this top ray, if it were to go straight through, well, we're speeding up again, so we're bending away from the normal. Now this top one, that would be if it went straight through without bending at all. If we're going to bend away from the normal line on that side of it, the angle has to get bigger with respect to the normal. So it's going to look like that. The angles get bigger with respect to the normal. Now for this lens shape, let me get that real quick. For this lens shape, it causes the parallel rays to spread out. And the really cool thing is that these spread apart rays look like they come from a single point. So we say they diverge from the focal point this time. So they're coming away from the focal point. That's different. Now, this is a concave lens, like we said before. That's just the shape. It's causing the light rays to diverge, so it's a diverging lens. And because the focal point's on the weird side, not like it was before, we're going to say it has a negative focal length. Now that's going to have some consequences. But just looking at what we saw here, when we work with lenses and these light rays, it kind of tells us how the light rays work. So we have some rules for ray diagrams, or for these little rays and lenses. The first one that we saw was that regardless of what kind of lens that we had, an incoming parallel light ray, those incoming parallel rays are refracted through the focal point, or as if they are going through, or as if they came from the focal point. The second one is that rays that pass through the focal point, rays that come in through the focal point, go out parallel, or rays that look like they are heading to the focal point go out parallel. That's just a reverse of the first one. Okay, so if parallel rays are focused to the focal point, rays coming from the focal point are bent parallel. And then the third one, any ray passing through the center of the lens doesn't get bent at all. So rays through the center don't bend. Now we're going to look at some examples of how to draw these, just two, and then we're going to do a whole bunch tomorrow. So, here's our example. We have to draw some things, and we need to talk about some terms. So this straight line that everything's done on is the axis of our system. The axis of the system must pass through the center of the lens. This is our reference point for everything. When we say something is parallel, it means it's parallel to this axis. So the axis must pass through the center of the lens. So let's draw the lens in there. And then we have a line that goes through the middle of our lens. It's really hard to draw lenses perfectly and then go back through and measure how things bend at the normal lines. We're not going to do that. We're going to have the plane of the lens, and we're going to say all the bending happens at the plane of the lens. Now, we also get to draw focal points. Here's my first focal point, here's my second focal point. And we have our object. And just so we're pretty clear on this, it's going to be important that these are positive focal points. So, the first ray that we draw, objects are going to be arrows for a while. The first ray that we draw is a light ray that comes in parallel to the axis and at the plane of the lens bends out through that positive focal length. So we're going to call this focal length F1. Okay? The parallel ray bends through F1. Our second ray goes through a focal point and comes out parallel. We're going to call this focal point F2. We could be done here, but just to show you, our third rule says we go in through the center of the lens and we don't bend. Now, this spot where all of the rays cross is where our image is. So the image is going to form where all of the rays cross. And we have some words for this image. This image is real, meaning that the light rays actually cross, meaning that I could project this onto a surface. That makes it real. It's inverted, which means upside down. And this image is magnified. It's bigger than the object. Those are the words that we're going to use to describe this image. Now, it being a real image doesn't make it different than the other kind of image. It just means that the rays actually cross there. Your eye can see it either way. So let's do our next example. This time we have an axis, but we're going to have the other kind of lens. We're going to have a diverging lens. So let's back up a little bit. These are negative focal points. So if F1 was on the right side of the lens for a converging lens, for a diverging lens, F1 is going to be on the other side of the lens, on the left side, and F2 is over here. That's what that negative thing does. It's the opposite kind of lens, so those focal points trade places. So for our first one, we're going to send a ray in parallel. And that parallel ray is going to look like it is coming from F1 this time. And it's important that it looks like it's coming from F1 because it's spreading out. And that's what we saw before. Now our second ray is going to look like it's heading through F2. But it's going to come out bent parallel to our axis. The third one is going through the center and nothing changes. Now if you look at these things, those lines, those light rays, will never, ever, ever cross on the right side of the lens. That means we have no real image here because the light rays don't actually cross. But when our eye sees something like that, our eye naturally traces that back to where it comes from. Those three lines look like they're coming from the same place. And so our eye sees an image there even though the rays don't cross. Our eye traces it back. And so for us to find it, we need to trace it back. And we'll go slower through that. Sorry. So to trace it back, let's trace back that ray, and let's trace back that ray. And we see that all three of those rays appear to be coming from the same spot. So let's put our image there. This image is formed where the rays appear to cross, appear to come from. And we can say some things about this image that are a little different than the other image. This image is virtual. Our eyes can still see it, but the rays don't actually cross there. They just look like they come from there. It's also upright, which means what it sounds like, and it's diminished, which is a fancy way of saying that it is smaller than our image. Sorry, smaller than our object. Those are the examples that we're going to look at here. We'll do more tomorrow. We'll talk a little bit more about this magnified and diminished thing. And then the next video we have, we'll talk about the little bit of math that we're going to put on this. But what's important for me is that you kind of know how to draw and find the images. So, that's it.